2, 1, 0.
Are we witnessing the emergence of a new space power as India's mission to the moon makes a terrifying discovery about the Earth's only satellite? If you want to know about the shocking discovery made by India that changes everything we know about the satellite and the future of moon missions, keep watching this video. Many people think of the US or Russia when it comes to space missions. While these two countries have intimidating spacefaring legacies, India has been making audacious moves in space exploration, and that did not start today. Back in 1962, under the Nehru administration, Dr. Vikram Sarabhai founded the Indian National Committee for Space Research, or INCOSPA, with the aim of shaping India's space program. Among the pioneering team of rocket technologists who laid the foundation of INCOSPA was Dr. APJ Abdul Kalam, who later became the President of India. Fast forward to 1969, a historic year when the Indian Space Research Organization, or ISRO, was born. The space agency was fueled by the vision of Dr. Vikram Sarabhai, hailed as the father of the Indian space program. India marked a historic milestone with the launch of the Aryabhata satellite in 1975, its inaugural venture into space. Named after the ancient Indian mathematician, the Aryabhata satellite was sent to conduct scientific experiments in X-ray astronomy, solar physics, and other realms. 1980 was another significant leap in the nation's space capabilities, with the launch of India's first satellite launch vehicle, spearheaded by Dr. Vikram Sarabhai and Dr. APJ Abdul Kalam. India launched its first interplanetary spaceflight mission, Mars Orbiter Mission, or MOM, also called Mangalyaan, on 5 November 2013 by ISRO. It made ISRO the fourth space agency to reach Mars, after the Soviet space program, NASA, and the European Space Agency. In fact, India has the distinction of being the first Asian nation to reach Mars orbit, and the first nation in the world to do so in its first attempt. India then turned its attention to the moon with its first lunar probe, the Chandrayaan-1, launched by ISRO on 22 October 2008. It was operated until August 2009. The mission included a lunar orbiter and an impactor. The vehicle was successfully inserted into lunar orbit on 8 November 2008. India then launched Chandrayaan-2 on 22 July 2019. It consisted of a lunar orbiter, lander, and rover, all developed in India. The main scientific objective was to map the location and abundance of lunar water. The most recent mission, Chandrayaan-3, was launched on 14 July 2023 and successfully landed on the moon on 23 August 2023. Thanks to these missions to the moon, India can claim a number of crucial discoveries about the Earth's only satellite. The Chandrayaan-3 mission, for example, marked a significant milestone in the history of lunar exploration when it became the first mission to successfully land near the moon's south pole, a region that has remained largely unexplored until now. The mission's primary objective was to demonstrate the capability for a safe landing and roving on the lunar surface. The spacecraft consisted of a lander named Vikram and a rover named Pragyan. The lander was designed to execute a soft landing on the lunar surface and to function for 1 lunar day, which is equivalent to about 14 Earth days. The rover, Pragyan, was a 6-wheeled robotic vehicle that was designed to travel up to 500 meters and leverage solar energy for its functioning. It was equipped with 2 payloads to enhance scientists' understanding of the lunar surface. Pragyan weighs 27 kg with dimensions of 0.9 meters by 0.75 meters by 0.85 meters. It operates on solar power with a power output of 50 watts. The rover is equipped with a rocker bogie suspension system and 6 wheels, each driven by independent brushless DC electric motors. Steering is accomplished by the differential speed of the wheels or skid steering. This design allows the rover to traverse the rugged lunar terrain. For navigation, Pragyan is equipped with stereoscopic camera-based 3D vision. It has two 1-megapixel monochromatic navcams in front of the rover to provide the ground control team a 3D view of the surrounding terrain and help in path planning by generating a digital elevation model of the terrain. Pragyan is unique because it is designed to operate on solar power and traverse 500 m on the lunar surface at the rate of 1 centimeter per second. It performs on-site analysis and sends the data to its lander for relay back to the Earth. The rover has made significant achievements since its successful landing near the lunar South Pole on 23rd of August 2023. It explored the moon using cameras and scientific instruments for nearly 2 weeks. During this time, it successfully traversed a distance of 101.4 meters. A major aspect of the mission was the landing site near the lunar South Pole. This region of the moon is of great interest to the scientific community due to its unique environmental conditions. For example, the extreme cold in the permanently shadowed areas could have led to the trapping of volatiles like water, providing clues to the history of the moon. The successful landing of Chandrayaan-3 near the South Pole opened up new possibilities for future lunar exploration, particularly in the polar regions. But what makes landing on the South Pole a huge deal? Landing a mission on the moon's South Pole is more or less navigating uncharted waters, where every step is fraught with unparalleled challenges and thrilling possibilities. This lunar region is a terrain of extremes, boasting some of the coldest, most rugged and shadow-drenched landscapes imaginable. The primary challenge in landing near the moon's South Pole is the terrain itself. Picture vast, shadowy craters and jagged, unpredictable surfaces that can make any landing attempt a high-stakes gamble. These areas are perpetually cloaked in darkness, hiding in the moon's eternal shadows, making them both fascinating and formidable. Navigation becomes a monumental task as sunlight barely reaches these parts, complicating visual guidance systems and making the reliance on onboard instruments and autonomous navigation systems absolutely critical. Temperature extremes add another layer of difficulty. In these shadowed craters, temperatures can plummet to a staggering -233 degrees Celsius. Such cold can freeze electronics and mechanical systems, challenging mission designers to develop innovative solutions to keep vital systems operational in conditions far beyond Earth's coldest winters. Notably, attempts have ended in heartbreak, with missions failing to land successfully, underscoring the difficulty of this lunar endeavor. For instance, India's Chandrayaan-2 lander and more recently, Russia's Luna 25 both crash-landed on the South Pole. The complexity of landing on the South Pole is as simple as it could get. It's tough to carry out a soft landing on the lunar South Pole. The Pragyan rover is credited with the groundbreaking discovery of recording the first-ever temperature profile of the lunar South Pole. This was achieved using one of the lander's payloads, the CHA-STE, or Chandra's Surface Thermophysical Experiment. CHA-STE is equipped with 10 advanced sensors and works on the basis of a controlled penetration mechanism that enables it to penetrate 10 centimeters below the top surface. The primary purpose of the CHA-STE device is to collect data on the thermal dynamics of the moon's surface by measuring temperature profiles of lunar topsoil near the pole. According to the data, the temperature of the lunar topsoil is roughly 122 degrees Fahrenheit or 50 degrees Celsius. However, the graph shared by ISRO depicts the temperature range from 14 to 140 degrees Fahrenheit or -10 to 60 degrees Celsius, depending on the depth. According to the graph, the temperature above the surface was roughly 122 degrees Fahrenheit, or 50 degrees Celsius, but it dropped to 14 degrees Fahrenheit, or -10 degrees Celsius, just 3 inches or 8 centimeters beneath the surface. This significant temperature variation with depth is due to the lack of an atmosphere, and it causes significant temperature changes on the lunar surface over its day and night cycle. The temperature on the surface was nearly 60 degrees Celsius, but it plummeted sharply below the surface, dropping to -10 degrees Celsius at 80 millimeters, or just about 3 inches below the ground. Why is this discovery crucial? It provides insights into the thermal behavior of the Moon's surface. Understanding the thermal behavior of the lunar surface is important for future lunar missions and potential human habitation. It can help in planning the design and operation of future lunar habitats and rovers. Moreover, the data collected by the CHASTE device can also provide valuable information about the presence of volatiles like water in the lunar soil. The extreme cold in the permanently shadowed areas could have led to the trapping of volatiles like water. Therefore, understanding the temperature variations with depth can provide clues about the possibility of the presence of water ice in the lunar soil. Another important discovery by the Pragyan is the detection of the presence of sulfur on the Moon's surface. This was achieved using the laser-induced breakdown spectroscope, or LIBS instrument, on board the rover. LIBS works by directing a laser beam at a target, creating a plasma. As the plasma cools down, the excited electrons settle, and the spectrometer reads the specific wavelengths associated with different elements, confirming their presence. The detection of sulfur is particularly noteworthy as it is a relatively rare element on the Moon. Sulfur usually originates from volcanic activities, and its presence on the Moon can offer valuable insights into the Moon's history and composition. The presence of sulfur in the South Polar region could indicate the existence of water ice, a crucial factor for future lunar missions and potential human habitation. Another reason the detection of sulfur is a significant achievement is that it provides insights into the lunar surface's elemental composition. Understanding the elemental composition of the lunar surface is important for future lunar missions and potential human habitation. It can help in planning the design and operation of future lunar habitats and rovers. Moreover, the data collected by the LIBS device can also provide valuable information about the presence of volatiles like water in the lunar soil. The extreme cold in the permanently shadowed areas could have led to the trapping of volatiles like water. Therefore, understanding the presence of sulfur can provide clues about the possibility of the presence of water ice in the lunar soil. Vikram, the lander, has also contributed massive to the expansion of our knowledge of the Moon, with the discoveries credited it to. However, the landing of the Vikram lander on the Moon was one of the most incredible and nerve-wracking moments in the history of space exploration. It was like the climax of the Chandrayaan 3 mission, so expectations were high. The Vikram lander was launched from Satish Dhawan Space Center in July 2023, along with a propulsion module. The propulsion module carried the lander and the rover to the lunar orbit, where they separated on 5 August. The lander then performed a series of orbit-lowering maneuvers to reach a 153 kilometers by 163 kilometer orbit around the Moon. The landing sequence began on 23 August at 17:33 IST, when the lander fired its engines to initiate the deorbiting phase. This phase lasted for about 10 minutes, during which the lander reduced its velocity from 1.6 kilometers per second to 0.1 kilometers per second and descended to an altitude of 30 kilometers. The next phase was the most critical and complex one, the powered descent. This phase involved 4 thrusters that controlled the lander's attitude and 4 thrusters that controlled the lander's velocity. The lander had to autonomously navigate through a narrow corridor of safe and flat terrain, avoiding obstacles such as craters and boulders. The lander also had to constantly adjust its trajectory and speed based on the real-time data from its sensors and cameras. The powered descent phase lasted for about 15 minutes, during which the lander performed 4 braking maneuvers: rough braking, attitude control, fine braking, and terminal braking. The rough braking reduced the lander's velocity from 0.1 kilometers per second to 0.02 kilometers per second, and its altitude from 30 km to 7.4 km. The attitude control oriented the lander's cameras towards the surface and performed a slight horizontal maneuver to reach the desired landing site. The fine braking further reduced the lander's velocity to 0.0014 km per second and its altitude to 400 meters. The terminal braking was the final and most delicate maneuver, which brought the lander to a hover at 100 meters above the surface. The lander then slowly descended and touched down softly on the lunar surface at 1803 IST. The landing of the Vikram lander was a remarkable feat of engineering and science, as it involved a high level of precision, accuracy, and autonomy. The lander had to overcome several challenges, such as the communication delay, the variable gravity, the uneven terrain, and the dust. The lander also had to cope with the extreme temperatures and the lack of atmosphere on the moon. The landing of the Vikram lander was also a moment of immense excitement and anxiety for the scientists, engineers, and the public who followed the mission. The landing was broadcast live by several media outlets and watched by millions of people around the world. The control room at the ISRO was filled with tension and anticipation, as the lander's status and telemetry were displayed on the screens. The landing was also witnessed by Prime Minister Narendra Modi, who was in South Africa for the BRICS summit. He followed the landing by video link and congratulated the ISRO team after the successful touchdown. The landing of the Vikram lander was a historic achievement for India and the world, as it opened a new frontier of lunar exploration. The lander deployed the Pragyan rover. The Vikram did successfully measure the density and temperature of the moon's ionosphere. In case you need an explanation, the moon's ionosphere is a thin layer of electrically charged plasma that surrounds the moon's surface. This layer is approximately 100 kilometers thick and is composed of a mix of ions and electrons. The Vikram lander made a name for itself by recording the first ever measurements of the density and temperature of the moon's ionosphere. The instrument responsible for these measurements was the radioanatomy of moon-bound hypersensitive ionosphere and atmosphere, or RAMBA payload, on board the Vikram lander. RAMBA is designed to measure the near-surface plasma environment and electron density in the lunar ionosphere. The data collected by RAMBA revealed a relatively sparse mix of ions and electrons in the ionosphere near the moon's south pole. This finding is significant as it provides valuable insights into the moon's ionospheric conditions, which are crucial for understanding the moon's atmospheric dynamics and its interaction with solar radiation. The temperature of the ionosphere is another critical parameter that influences the behavior of the plasma. The temperature affects the speed of the ions and electrons, their collision rates, and the overall dynamics of the plasma. By measuring the temperature of the ionosphere, the Vikram lander has provided valuable data that can help scientists understand these dynamics. The measurement of the ionosphere's density and temperature is a challenging task due to the thin and variable nature of the ionosphere. The density and temperature can vary depending on the time of day, the lunar cycle, and solar activity. Therefore, the successful measurement of these parameters by the Vikram lander is a significant achievement. These measurements are not only important for understanding the moon's ionosphere, but also have implications for future lunar missions. The ionospheric conditions can affect the performance of communication and navigation systems of spacecraft operating in the vicinity of the Moon. Therefore, accurate knowledge of the ionosphere's density and temperature is crucial for the design and operation of these systems. In addition, the data collected by the Vikram lander can also contribute to our understanding of other celestial bodies with similar ionospheric conditions. By comparing the data from the Moon with data from other bodies, scientists can gain insights into the processes that shape the ionospheres of different celestial bodies. Another discovery credited to the Chandrayaan-3 mission that is literally groundbreaking is moonquakes. Moonquakes are seismic events similar to earthquakes on Earth that occur on the surface of the Moon. They were first detected between 1969 and 1973 after Apollo astronauts placed seismometers at their landing sites around the Moon. The detection of moonquakes is significant as it provides valuable insights into the Moon's interior and tectonic activity. The Chandrayaan-3 mission achieved its discovery using the Instrument for Lunar Seismic Activity, or ILSA payload, on board the Vikram lander. ILSA is a high-sensitivity accelerometer that measures vibrations on the Moon's surface. On August 26, 2023, ILSA recorded an event that appeared to be a natural moonquake. The source of this event is currently under investigation by scientists. The detection of a moonquake is a significant achievement as it provides insights into the Moon's seismic activity. Understanding the Moon's seismic activity is important for future lunar missions and potential human habitation. It can help in planning the design and operation of future lunar habitats and rovers. Moreover, the data collected by ILSA can also contribute to our understanding of other celestial bodies with similar seismic activity. By comparing the data from the Moon with data from other bodies, scientists can gain insights into the processes that cause seismic events in different celestial bodies. The detection of a moonquake also has implications for our understanding of the Moon's geological history. For instance, moonquakes can provide clues about the Moon's interior structure and the processes that have shaped its surface over billions of years. In addition to detecting a moonquake, ILSA also recorded vibrations caused by the movements of the Pragyan rover and other payloads. These measurements can provide valuable information about the interaction between the lunar surface and the rover. The data collected by the mission will provide valuable insights into the lunar topography, mineralogy, elemental abundance, lunar exosphere, and signatures of hydroxyl ions and water ice. The findings will be crucial for the future planning of scientific missions to the Moon. The discoveries made by the Chandrayaan-3 on the Moon build on the success of earlier lunar missions. For example, the Chandrayaan-1, India's first lunar exploration mission, launched in October 2008, and among its many achievements was the detection of cliffs and signs of displaced underground rocks in 2 craters near the lunar South Pole, which could indicate the presence of water ice and tectonic activity. The instrument that was responsible for these findings was the Moon Mineralogy Mapper, or M3, a hyperspectral imager that was provided by NASA as a part of the international collaboration. M3 was designed to map the mineral composition of the lunar surface by measuring the reflected sunlight in different wavelengths, from visible to near-infrared. M3 had a spatial resolution of 140 meters per pixel and a spectral resolution of 10 nanometers. M3 operated from November 2008 to August 2009, during which it collected more than 9 terabytes of data, covering about 95% of the lunar surface. One of the regions that M3 focused on was the South Polar area, which is of special interest because it contains permanently shadowed regions that could harbor water ice and other volatiles. M3 scanned the South Polar area at different local times to capture the variations in illumination and temperature. One of the craters that M3 observed was Shackleton, a 21-kilometer-wide crater located at the lunar South Pole. Shackleton is mostly in permanent darkness, except for its rim, which receives sunlight for most of the year. M3 detected a sharp contrast in reflectance between the sunlit and shadowed areas of Shackleton, indicating a difference in surface composition. M3 also detected a bright spot near the center of the crater, which could be a patch of exposed bedrock or a deposit of ice. Another crater that M3 studied was Haworth, a 34-kilometer-wide crater located about 150 kilometers from the South Pole. Haworth has a complex morphology with a central peak, terraced walls, and a flat floor. M3 detected several spectral features in Haworth that suggest the presence of different minerals, such as pyroxene, olivine, and spinel. M3 also detected a high reflectance area on the eastern wall of Haworth, which could be a cliff or a landslide. The detection of cliffs and signs of displaced underground rocks in Shackleton and Haworth craters by M3 has important implications for lunar science and exploration. These features could indicate the presence of water ice and other volatiles, which could be used as resources for future missions. They could also indicate the occurrence of moonquakes and tectonic activity, which could provide insights into the thermal and geological evolution of the Moon.